To speed up the process and to shorten this video, I've only shown you the derivation, the mathematical derivations of the time from the Schrodinger equation to the time-independent Schrodinger equation. I will not just read it out and then explain the terms, because you can actually find this from many standard quantum mechanics introductory books, which I've given some references to. So this can shorten the and this because some disturbance from some noise outside noise, so I don't want to read it and then being disturbed by the noise. And all this you can find from the introductory quantum mechanics books, which I've referred later to later. I've got all these just from the some introductory quantum mechanics book. One is called Quantum Mechanics, a Complete Introduction by Dr. Alexander Zagorski. This is a 2015 edition from on page 78 to 79. And another of this introduction book is called Quantum Mechanics Demystified, the 2005 edition from page 116 to page 18. It's by David Mahon, and I've got some of the materials which the history concern the history of the Schrodinger equation, and also the de Broglie matter wave theory from the book called the Dancing Woolly Master, which is a rather old book, 1979, by Gary Shukov, from on page 122 to page 128. And remember that I have some note on the Oppenheimer-Volkoff Equation. The note is that the star or stellar structure mentioned in that section also includes the Jeans mass of the dark matter halo, which you can find from my video 3 of my series. And also there's some clarification that here we use the sine x square, the x square. Actually, the x is equal to r in this former section of the general relativity of the Oppenheimer-Volkoff equation. X is equal to r, is equal to the distance to the center of mass of the quantum system. Also here, x dx square dx. This means differentiate x to the power 2 twice. X to the power 2 twice. The 2 here means twice. When you, and this is something you have to clarify here. From my video 2, we know that x bar is just equal to mc x or r. We have explained x is to r. This x here is equal to the r in the previous section on Oppenheimer equation, r. Right? It's just the same, different notations. And when it is x bar is equal to mcr x or r, then you get it substitute here becomes e psi x, e phi x is equal to just m square c square d square. Is x bar square, so mcx becomes m square c square and x square here. So m and cancel m, so and it become mc, and this dx square, this dx twice is just equal to 2x, that's the number 2. So cancel with this 2 here, just mc square. You get the result. So with b, if this is b, mc square b, this is just equal to a here. The result from the Oppenheimer-Volkoff equation A is just mc square. R means nothing. That means m is a function of r. That's all. It's actually m is, you can ignore the r. So if this result from the Volkoff Oppenheimer equation is equal to a is equal to mc square, and then the result in B is from the time-independent Schrodinger equation is just equal to mc square. So A is equal to B. So that is to say, when the same or equivalent quantum particle, that is to say equivalent means equal mass, equal charge, etc., are being considered, and for example, a hydrogen atom, a neutron, electron, etc., the treatment using theory of general relativity. The Oppenheimer equation is strictly derived from the general relativity. And then the treatment using the quantum mechanics under the Schrodinger equation, the results are the same. The final results are the same. This we got a strict proof of the general relativity is equal to and strict proof of the equivalence, as we say, equivalence of general relativity to quantum mechanics. So I've finalized my video here because I have to bleach it a lot because there's a lot of noises. It's disturbing when I'm talking.